All right, so this week we're going to go over Chapter 10, which is the Alcohols Reactions Unit or Chapter. And like I said before, earlier, it's roughly about the same amount of reactions as alkenes and alkynes. Chapter 10, some people find a little bit more challenging, but I think once you guys get the hang of it, it should come fairly quick to you guys. All right, so pretty much we are going to start out with a alcohol or end with the alcohol, and majority of these reactions, and then later on we'll get to thiols. And a quick side note on what a thiol is. H is what a thiol is. OH is alcohol. And hopefully, if you guys didn't know already, CH3O is methanol, and then CH3, CH2, OH equals ethanol. Okay? And then this is what ether looks like. Oh. Okay. Ether is like an oxygen with two R groups on the side. You can kind of think of it as ether is very similar to the word either. So like either or. Okay. So in OChem 2, you guys will actually discuss ethers and esters reactions, which kind of also deal with alcohols. So everything you're learning in this unit is very important because they will show up. Sorry, not this unit. This specific chapter, chapter 10, will show up next semester as well. So when you're transitioning from OChem 1 to OChem 2, the reactions you want to review. But when you get to OChem 2, of course, they will go over it again. All right, so first up, we have just a simple way of going from OH. Let me zoom in a little bit. So you are going from alcohol, and your reactions are number 1, NaH, and then number 2, you have CH3 iodine, or let me put bromine. Okay. So first things first, this should be a quick review from last unit. This NaH is a strong base that deprotonates this H to turn this alcohol into a good nucleophile, which then will attack this methyl bromide, which will kick off the bromine, and then we'll add a methyl on the right side of this O, and you end up with a structure that looks like an ether. Okay. All right. So slightly uncommon, but that's one of the reactions. All right. Just like NaH, you might also see NaOH. So don't be alarmed if you see either or. LDA is also another good base. All right. So now we are actually going to go over one of the main reactions in this chapter, which is called Grignards. Okay. And I'll draw out the reaction and I'll type it out, the name. So we are going to have a benzene ring. And instead of 3 double bonds, just pretend that. And then we have bromine here. All right, now the reaction is Mg, and Mg is always paired with ether as its solvent. Okay, and we just went over what ether is, so hopefully you guys know that. It's not essential to, I guess, solving the problem. Just understand that these two are always paired together. And Mg will attach itself next to bromine, and it will just turn into the same exact reaction. So instead of benzene bromide, we have benzene magnesium bromide. Okay, so nothing fancy going on here. This should be a very fairly simple, straightforward step. Okay, so once we have created this, this is the start of our Grignard reagent reaction. Okay, and I'll type that out. So it's Grignard. Okay, so once we have this, we could attack. This is essentially a nucleophile. Okay, so some key notes about Grignards are it's the base. That's R group plus MGBR is always going to be a base. And yeah, like I said, Grignard, anytime you see a R group bonded to MGBR, that indicates that you have a Grignard reaction occurring. And typically it is split with a negative charge for the R group and a positive charge for the MGBR. Okay, R is your nuke. Okay, so the whatever is attached to the MGBR, that is what you will attack with. Okay, and in this unit, you will attack most commonly a ketone. Okay, and a ketone, a nucleophile attacking a ketone might be odd to you, you know, coming in from last unit, but there is a carbocation that we can get from. Okay, I think I mentioned a dipole moment in previous weekly reviews, so if you guys remember, carbonyl creates a dipole moment between the carbon and oxygen, because oxygen is, as you know, more electronegative than carbon. So we have a partial positive charge here. And partial negative charge here as the oxygen attracts and inducts those extra electrons from carbon. Okay, so this dipole moment that we have created or that exists in a ketone is not susceptible to any nucleophilic attack such as a Grignard. Okay, so don't think nucleophiles as in the original sense that you guys are used to, like SN1, SN2. Think of this as your, like a benzene ring is your nucleophile. Okay, so we split right here. The negative charge is right here. The positive charge is here. The positive charge leaves as your quote-unquote leaving group. Let me fix that. Okay, and then this negative charge will come in and attack right here. Okay, So when that happens, let me draw out the result. So we still have our benzene ring. And then I'm going to draw your new bond in orange. And then here are your two methyls on both sides. And then here is your carbonyl. Okay, does anyone see what's wrong with this reaction and what we have to do? If you guys know, let me know in the chat. Any ideas? All right, well, so pretty much the most important rule in OCHEM, quote unquote, is carbon has 5 bonds. Okay, we never want carbon to have 5 bonds. We always want carbon to be stable. It wants 4 bonds, and yeah, and no charges. So because of that, we are going to have to get rid of one of these charges. We have to place those extra electrons somewhere else. Okay, and that somewhere else just happens to be our electronegative atom. And that's okay because oxygen is electronegative and it gladly will accept those extra electrons. And when that happens, we end up with, so let me redraw this. So we're just going to go over here. So we have our benzene ring. Okay. And then our bond, and then this bond, and then now instead of a double bond, we have a single bond. And then oxygen gained 2 electrons because 1 bond equals, remember, 2 electrons. And then if you guys remember, 2 electrons or a lone pair is also sometimes denoted as a negative charge. Okay, so we will place a negative charge on oxygen rather than carbon. Okay, and as you guys remember from the very first unit, it's more stable to have a charge on oxygen, nonetheless a negative charge on oxygen rather than a carbon. Okay, so we have a question, why couldn't you flip the way it was originally attached? Why couldn't you flip the way it was originally attached? Can you elaborate? I'm not sure I quite understand your question. Like, why did I angle it this way instead of attacking this way? Okay. I just did it to, I guess I thought it would be clear to see that it's attacking the middle. Because regardless if I attack from this way or this way, I'm still attacking that carbon. I just thought this way would be easier to see what's happening. But yeah, it's the same thing. All right, so we are left with this structure here. Okay, now in organic chemistry, and for the purpose of this class, there is something called proper workup. Okay, uh, hopefully you guys heard of this. And proper workup basically means whenever we have a negative charge, typically next to an oxygen, we assume that there is water molecules in the solution that can donate one of its protons to the negative charge to satisfy the imbalance of charges. Okay, so in your final answer, it should look like this. Okay. And what do you know? We have a alcohol at the very end. Okay, so Grignard reactions will, um, I'm pretty sure I can use this word. Um, it will always lead to a tertiary uh, OH. Okay. Um, if it doesn't, that means you can do it again. And we will talk about a scenario where you have to do multiple additions of Grignard. Okay. Um, and yeah, I guess just, always is a very tricky term in any subject. So, most of the time, at least I haven't seen a scenario where Grignard reactions did not lead to a tertiary alcohol. Okay, so if you see MGBR in your starting reaction and then you end up with a tertiary alcohol, or you end up with a carbonyl, or your alcohol is on a primary or a secondary bond, that means something might have gone wrong and you might want to check your work. Your answer choices will definitely have all of those tricky answer choices to throw you off. So just remember, that's one of the benefits of multiple choice. You can eliminate some obvious answers. Okay. Now I'll go over a scenario where you have to do multiple additions of Grignard. I'm going to start from here. Instead of a ketone, I am going to use a so first of all, instead of a benzene ring, this time I'm just going to denote this as R. Remember, R could literally be any carbon to carbon structure, or just anything. Okay, MGBR. Okay, we cleave off the MGBR, and then our R will attach to a carbonyl. Okay, but instead of a ketone, I am going to use a acid chloride. Okay, and acid chloride is, you have a methyl, a carbonyl, and a chlorine. Okay, so I chose this one, and I can also have chosen, that's an or, I can also have chosen a ester, which, as you know, is a OR group at the very end. Okay, I chose these two because these two are good leaving groups. Okay, this is very easy to leave and place a carbocation charge right here. Okay, so let me write that down. Good LGs. I should probably not abbreviate. Okay. So we're gonna go over a scenario where you have a Grignard reaction on attacking a good leaving group structure. Okay. And then for this purpose, you can have a ketone, or another common one is an aldehyde. So aldehyde works in the very exact same way. Instead of two ketones, instead of two methyl groups, you will have one methyl group on one side and a hydrogen on the other side. So these are interchangeable. Okay. So for these two, Grignard will only attack once. Okay. So attack once. Okay. For good leaving groups, we attack twice. Okay. All right, and I will explain why we have to attack twice or react twice. Okay. So I'm gonna use the chlorine again, and let me draw it right here. So when I attack, I have a methyl there, a chlorine here, and my carbonyl right here, okay? And as we said, carbon cannot have 5 bonds. One of those bonds must leave, okay? Now in the first reaction, we chose the carbonyl double bond to go to oxygen, okay? That's because we had no other option. There was literally no better option. But for here, we have a methyl group, we have a oxygen, and we have a chlorine. Now chlorine, as you know, is a very, very good leaving group. And so instead of oxygen taking the negative charge, it will get rid of that extra bond. The carbon will get rid of that extra bond by chlorine leaving. Okay, so chlorine leaves. Okay, so what happens? What does our structure look like when chlorine leaves? Well, we get something that looks like this. So we have R, and then we have methyl, and then we have our carbonyl. Okay, well, we still have that partial charge, right? The whole reason Grignards can attack these structures is because carbonyl creates a partial positive, partial negative dipole moment, okay? So we didn't get rid of that dipole moment, so that's why we have to attack again, okay? And I'll draw that right here. So when we attack again, remember, the R group is already there. One R group is already there. When we add a second R group, it looks like this. So both R groups are the same molecules, same structure. So instead of the R group, pretend it's a benzene ring, okay? These should be the exact same structures. It should not be like a benzene ring here and like a methyl group here or like a propyl group here, okay? Because you're still using the same R MGBR, okay? Now, once again, we can't have this, so that's why now it has to go onto the oxygen, okay? So regardless of what we do, we will always end up having a negative charge on oxygen, which in turn always becomes into a alcohol. Now if I write it out, it will look like this. Okay, and what do you know? It's a tertiary alcohol. Okay, so always remember that fact. Uh, tertiary, tertiary. Okay. All right. So, do you guys have any questions on how Grignards work? Because honestly, knowing how Grignards work is really important reaction for Chapter 10. I know you guys don't have a exam just for this unit, but I would really not be surprised if it shows up on your final exam. Okay? So any questions on how this works? Okay, that's fine. Well, hopefully when you get to Grignards, you will know what to do. Now that I explained it, if you want to, if your professor hasn't gone to alcohols yet or just started, I guess go through a little bit more lectures and then come back to this weekly review and hopefully it will click better. But for now, I'm going to go over some of the other reactions. So MgBr can also, let me zoom in a little bit. Okay, I'm going to use the right side. So let's say you have this structure, and you have MgBr here. Okay. Now let's say that is attacking an epoxide. As you guys remember, an epoxide is the triangle looking thing with oxygen on one side and carbons on two other sides. And then I also have a methyl group here. And then at the bottom, I have acidic water, which can be denoted as H3O+. Okay? All right, so as you guys know, Grignards are bases because I just told you in the other slide, or yeah, right here. Okay? And because it's a base, and we are attacking this, actually I'm getting ahead of myself. So Grignards are basically bases, but they act as a nucleophile. Okay, they're essentially, I mean, if you had to think of it as a good base and a good nucleophile. Okay, this nucleophile is going to attack either this carbon or this carbon because we have another dipole moment. Okay, but this time we have two options. Okay, because our attention is getting split in two different ways, right? Epoxides will always have this notation, okay? But the thing is, on the left side, we have a primary carbon. On the right side, we have a secondary carbon, okay? Primary because this carbon is only bonded to one other carbon. Remember, you don't count the oxygen. And then, but the right carbon is bonded to two other carbons. This carbon is bonded to this carbon and this carbon, that's why it's secondary. So this is more substituted, okay? And I'm not sure if I've mentioned this before in these weekly reviews, but there is a acronym to remember which side you attack. It's called BLAM, and that stands for basic equals least sub, and acid you attack the most sub. Okay. All right. So now that we know that, and now that we know Grignards are bases, we are going to attack this side, which is the less substituted side. Okay. And once again, I'm gonna draw this, and I created a new bond. Okay. Actually, I'm gonna flip the methyl group. It doesn't change anything, so don't freak out. So when I created a bond right here, this bond will sever. Okay, so whichever side I'm attacking, the epoxide, that bond to the oxygen will cut off and cleave because same rule as carbon will have too many bonds, because carbon has two bonds here because two hydrogens, one bond to the oxygen, one bond to the carbon, and then a new bond to this R group. So that's 5 bonds, which is why it has to cleave its bond, and those electrons will actually go to oxygen, just like how we did in the carbonyl. Okay, just like this. This is the exact same scenario. Okay, it's just one's a carbonyl and one's an epoxide, but everything's the same. So if you guys know everything's the same, then eventually we have to end up with a tertiary alcohol, right? Because that's the hidden rule of Grignards. We end up actually, I take that back. Okay. Yeah, this is the reason why it's not it's not guaranteed to be a tertiary alcohol all the time. It's only a tertiary alcohol when we are attacking some type of carbonyl. Okay, but if we're attacking a epoxide, it does not have to be tertiary, but it does have to be an alcohol. Okay, it just depends on how many methyl groups we have. Okay, so it looks like this. Okay. And yeah, the acidic water basically to help with the proper workup to turn the O negative to OH. Okay. So as you guys know, there were two sides to this epoxide. One side you attach the R group, and whatever side you didn't attach the R group, which is the right side in this case, will automatically turn into OH. We won't have that triangle anymore. This is called attacking the epoxide and opening the, it's like the formal name is like opening of an epoxide or something, like on your lecture slides. And yeah, this is kind of like the mechanism on what happens. Okay, any questions on that? Okay, if there are no more questions, all we have left are the reducing agents. Okay, and you might have not gone to that yet either, but I will go ahead and complete that last round of reactions. And just remember, we also have a weekly review next week, which is going to be our last weekly review of the semester for OCHEM 1. And next week will also be the last week of peer tutoring, but we only open Monday, Wednesday, Friday. Sorry, Monday, Tuesday, Wednesday. My bad. We are only open Monday, Tuesday, Wednesday next week. And of course, the times are 10 to 8. And yeah. So, any last minute questions you guys have about anything over the semester? Next Wednesday at 8 will be the final time. Okay. So, next Wednesday during my weekly review, I will go over any questions you guys have. So, yeah. All right. So, back to our lesson. The final set of reactions of this unit are reducing agents. And yes, okay, someone said, I'm not sure if you said it, but is peer tutoring have a final exam review? I'm not sure about a final exam review, but my weekly review next week will essentially be a Q&A kind of review, not your typical, like, I go over all the topics of the semester. Okay, so just keep a lookout on your e-learning or emails to see if there is a week an exam review rather, where tutors go over random topics. But yeah, but if you come prepared with questions next week, I will be gladly going over anything over the semester. All right, so let's run through these reducing agents and we can end the review. So the first one is NaBH4. This might look familiar because you used it in the oxy demercuration one. where you reduced one of the triangle sides of mercury into a simple hydrogen. And then you have LaH, which is the best one that you will always use. And then you have Radium nickel. And then you have something that I've already talked about and you guys should be familiar with, which is just a simple hydration using PT or PD or Ni, which is nickel. Okay, so I think it's, yeah, PT, PD, or Ni. Okay, so all of these are reducing agents, but all are not created equally. Some are stronger than the others, just like oxidizing agents and just like cleaving strengths. So I'll explain or I'll show you what each of these can do. NABH4 can reduce ketones. So if you see a ketone and NABH4 is the reagent that you're using, it will reduce to a secondary alcohol because it's in the middle. And if it can also reduce aldehydes. Sorry, I know that's kind of small. But that's an aldehyde, and it will reduce it into a primary alcohol. Even though the H is right here, they don't always draw the H. Okay, yeah. So that's the same thing as drawing it like this. Okay, because the H is just right there, but it's not always drawn. Okay, so NABH4 will only reduce ketone and aldehyde. Okay, if it reduces a ketone, it will turn it into a secondary alcohol. If it reduces a aldehyde, it will turn it into a primary alcohol. And like I said, because it's multiple choice, they will give you both options, like secondary and primary, or tertiary even. So just be prepared. Okay. LAH can reduce a lot of things. Let me just double check to see everything it does. Sorry, give me 1 second. All right, sorry about that. Okay, so it will reduce, and I'll just type these out. So it can do ketones, it can do aldehydes. So those are just same thing for like NABH4. It can also do esters and carboxic acids. Now this I will draw out so you guys can see. So esters, when it gets reduced, it will look like this. So it will actually get rid of the OR and the carbonyl. So you end up with just a primary alcohol. Okay. And carboxylic acids, I believe you get 2 alcohols because you're just reducing the carbonyl. Or yeah, give me one moment to double check all that. All right. Yeah, no. You don't get 2 alcohols, you just get the primary alcohol, just like ester. It'll just cleave off the carbonyl. Ester will also just cleave off the carbonyl and turn OR into OH. Same for amide. This is LAH. Here, I'll just write. So ketones, aldehydes, esters, carboxylic acid, amide. Okay. So LAH can pretty much do most things. Okay. Now rainy nickel can do ketones, aldehyde, ides, and it can also do double bonds. Okay. And hydration can do triple and double bonds. Okay. So that's a very quick summary of it, of all your reducing agents. Any questions on any of these? I'm not sure if you guys ever had matching, but I would assume, reducing agents could have like matching. At least that's what I had. But obviously things have changed. So this might be in a multiple choice format. Okay. I'm trying to see if there's anything else that I'm missing as far as reactions go. No, that should be it. If there's anything else, I would just refer to your lectures. If there's any single reactions that I missed, most of them I've covered. Obviously, they can change up the reactions a little bit by some slight variation, but the principle should still apply. Just don't forget, let me zoom out, just don't forget how the mechanism of Grignard works. Like I said in the very beginning of this unit, mechanism isn't important for every single reaction, but it does help you understand. And for some specific reactions, you should definitely know how the mechanism works. And Grignard is definitely one of those that you don't want to just simply memorize. Okay, you want to know how works. So in case of a ketone versus aldehyde, you know whether to attack once or twice, okay? Because you know the mechanism. If you didn't know the mechanism, you would just leave it like this or put alcohol right there and chlorine right there, okay? And then just like ketones, aldehydes, acid chlorides, and esters, epoxides work the same in that Grignards will attack here, okay? And yeah, remember all these key points. And then yeah, this is kind of a murky statement. If attacking currently, okay? All right. Any questions over this chapter or anything at all of Unit 3? I know you guys still have a long way before your final exam, but hopefully next week's review, if you guys have any questions, we'll clarify anything. Maybe I'll just write down the topics and so you guys can know what to ask questions on. All right, but if there's nothing else, I will end it here. Thanks for coming, those of you joining me live, and those of you who are watching the video. I will see you next week. If not, good luck on your final exams. And just a little side note, I will do, or I'm not sure, but there will be weekly reviews for OChem 2. So if this semester has full, make sure to join next semester too. And yeah, just stay tuned for more information on that. All right, well, have a nice week.